Hi everyone, I'm Veerbasant Reddy. Today I and Madhurima will be discussing some topics related to CUDA architecture. We all know GPUs and CPUs, and GPUs has provided a huge edge over CPUs. The primary reason we want to use GPUs is that the extremely computational power that they offer. There are two major advantages that the GPUs have over CPU is tremendous computational throughput and extremely high memory bandwidth. Like CPU, that is central processing unit, it is a single chip processor, and the GPUs has hundreds of cores as compared to 4 or 8 in the latest CPUs. The primary job of the GPU is to compute 3D functions. Because of these types of calculation, they are very heavy on CPU. The GPUs can help the computer run more efficiently, and GPU came into existence for graphical purpose. It has evolved into computing precision and performance. The evolution of GPUs over the years has been towards better floating point performance. That is, NVIDIA introduced its massively parallel architecture called CUDA in the year 2006, and changed the whole outlook for general purpose GPUs programming. The CUDA architecture has a number of processor cores that work together to munch the data sets given an application. The GPUs use the GPUs to do general purpose scientific and engineering computing. The model of the GPU computing is to use CPU and GPUs together in a heterogeneous co-processing computing model. We will be discussing the heterogeneous model in the upcoming slides. The sequential part of the application runs on the CPU, and the computational intensive part is accelerated by the GPU. This figure is the core comparison between the CPUs and GPUs. Has CPUs has less number of cores when compared to GPUs. GPUs has hundreds of cores. These are the differences between the CPU and GPU. That is, CPU can be optimized for high performance on sequential codes, whereas GPUs can be optimized for higher arithmetic intensity for parallel nature. And CPU provides a task parallelism, and GPU provides data parallelism. Whereas, like CPU has high performance on single thread of execution, whereas GPU has high throughput on parallel tasks. And like CPU has a high branching granularity, whereas GPU has fast access to onboard memory, and it runs a program on each fragment, whereas in CPU we can see that there are lots of different process and threads. This graph illustrates how the computational throughput of NVIDIA and Intel processors have increased over the past few decades, which is measured in units of billions of floating point operations per second, and a green line represents NVIDIA's flagship, that is GPU, at different points in time, whereas the blue line represents Intel's flagship CPUs at different point in the time. If we focus on GeForce GTX Titan, we can see that the amount of computational throughput offers us is almost an entire order of magnitude greater than Intel. The reason behind this inconsistency in floating point capability between GPUs and CPUs is that GPU is specialized for compute intensive, highly parallel computation, that which is exactly what graphics rendering is all about. In It is designed in such that like more transistors are devoted to the data processing rather than data caching and advanced control logics. Here we'll be discussing general purpose graphics processing unit. Usually the GPUs are the processors that can operate in parallel by running a signal kernel on many records in a stream at once. A stream is simply a set of records that requires similar computation. Stream provides data parallelization. By using GPUs for processing for non-graphical entities is known as general purpose GPUs. If we use GPUs for computational intensive tasks, then this kind of work is known as general purpose GPUs. The arithmetic power of GPU is a result of highly specialized architecture. This This specialization results in intense parallelization, which can lead us to great advantages if it is used properly. But this architecture comes at a price. As a result of parallelism in general purpose GPUs can't handle integer data operands, bit shift and bitwise operations, and double precision arithmetics. As we all know, the main purpose of GPUs is parallel execution on multiple data elements. As parallelism is obtained by rearranging the data from scalar quantities to vector ones. At present, CUDA is a predominant method for general purpose GPUs acceleration, although it is only supported by NVIDIA's GPUs. In longer term, like OpenCL promises to become a vendor neutral standard for programming heterogeneous multi-core architectures. As it is a largely based on CUDA, there will be hopefully be relative little difficult making the switch from CUDA's prosperity APIs to APL. Here we'll be discussing the CUDA architecture. Like as CUDA is a parallel computing platform and an API model, that is application programming interface, it is basically an extension of C and C++ programming. CUDA is a programming language that uses, that is, we all know, that is graphical processing unit, and CUDA gives us an advantage of massive computational power for us. This massive parallel computation power is powered by NVIDIA's graphics card. It has some extensions to that language to use GPU specific features that includes new API calls and some type of qualifiers that apply to functions and variables. This figure shows the CUDA architecture. There are two main pieces of hardware in this CUDA programming model, that are CPUs and GPUs. Each of their own has a dedicated memory region. The CPU together with computer RAM is referred to as host. Similarly, the GPUs together with its own dedicated DRAM is called device. As I said, this is the CPUs and the GPUs. The host, that is CPUs, and it has its own memory, is known as host, and the device, that is host and device. And the heterogeneous architecture is a combination of both host and a device. The CUDA model has three basic parts, that is grids, blocks, and threads in a hierarchical structure. There are a number of threads in one block and the number of blocks in one grid, and a number of grids in one GPU. CUDA has some specific functions called kernels. A kernel can be a function or a full program invoked by the CPU. The CUDA also provides shared memory and synchronization among threads. CUDA is supported only on NVIDIA's GPU based on Tesla architecture. These graphic cards that supports CUDA are GeForce 8 series, Quadro, and Tesla. Here we'll be discussing the grid, the block, and the thread. The grid is a group of threads all running on the same kernel. These threads are not synchronized. Like every call to CUDA from CPU is made through one grid. The blocks are The grids are composed of blocks. Each block is a logical unit containing the number of coordinating threads. Just as grids are not shared between GPUs, blocks are not shared between multiprocessors. All blocks in grid use the same program, a built-in variable, that is block IDX, that each has their own ID values, can be used to identify the current block. The block ID can be, that is, of one dimensional, 1D, or 2D, that is grid dimensional. Usually there are 65,535 blocks in GPUs. The blocks are composed of threads. The threads can run on individual cores of multiprocessors, but they are not restricted to single core. Like blocks, each threads has their own ID, that is thread ID, that can be like 1D, 2D, or 3D. That is block dimension. The thread ID is related to the block it is in. The threads have certain amount of register memory. Usually there can be almost like 501 to 512 threads per block. This is the memory model for CUDA architecture. It has different types of memories, that is shared, constant, cache, texture cache, and device memories, that is global, constant, and texture. Here, like all multiprocessors can access large global device memory for both gather and scatter operations. Like memory models, here this memory model is relatively slow because it does not provide caching. Here, like both CPUs and GPUs have separate memory spaces, as the data that is being processed by the GPUs must be moved from the CPU to the GPU before the computation starts, and the results of this of the computation must be moved back to the CPU once processing is completed. The global memory, in this memory is like accessible to all the threads as well as that is host, that is CPU. The global memory is allocated and deallocated by the host, and it is used to initialize the data that the GPU will work on. This figure shows like the shared memory for thread blocks, that is each thread block has its own shared memory, and that is accessible only by the threads within the blocks, and they are much faster than local and global memories. It requires like special handling to get maximum performance, and only exists for the lifetime of the block. Here it is. This figure shows like the local memory for thread. Like each thread has its own private local memory, only exists for lifetime of the thread, like generally handled automatically by the compilers. And the other one is like constant and the texture memory, they are like read only memory space that is available accessible to all the threads. The constant memory is used to cache values that are shared by all functional units, and the texture memory is optimized for texturing operations provided by the hardware. This is the heterogeneous architecture for CUDA architecture. The NVIDIA's graphic cards is that provides an extreme multi-threading computing architecture. It consists of like a set of parallel multiprocessors that are further like divided into many cores, and each core executes instruction from one thread at a time. Here, like in for heterogeneous architecture, is like it is a combination for both serial and parallel execution. The parallel execution is expressed by kernel function that is executed on a set of threads in a parallel on GPU. The number of threads blocks and the number of threads within the blocks that execute this kernel is parallel, and which are given explicitly when the function is called. The kernel function can only be invoked by serial code from CPUs. To call the kernel function, the execution configuration must be specified. That is, that the number of threads in the thread blocks and the numbers of threads within the grid. Like to declare the grid and thread blocks, CUDA has like predefined data types, that is dim3, which is an like integer vector type that specifies the dimensions for grid and thread blocks. In the kernel function call, the grid and block variables are written in like three angular brackets, which has like grid and blocks. Like in this invocation, like the thread grid and the thread blocks are created dynamically. The value of the grid and the block variables must be less than the allowed size. The kernel function has always returns a type that is void. It has a qualifier that is global. That means that this is a kernel function that is to be executed on GPUs. We will be discussing about these qualifiers in the later slides. There are many myths about CUDA. Like the GPUs are the only processor that in the CUDA applications. Like we all know that CPUs and GPUs can work together in CUDA applications, and GPU has a wide range of very wide, that is SMID machines. That the CUDA has that is SMIT machines, which wraps around like 32 threads. And we know that, and there is one more myth, that is branching is not possible on GPUs. Actually, it is incorrect. It is possible and can be implemented very easily. The CUDA is only for C and C++ programmers, but it can be also used for programming languages such as Java and Python. That's all I have. Like I'll pass it over to Madhurima.
To continue with the presentation, this is the processing flow of CUDA. GPU helps in parallel processing. GPU has its own local memory unit. So first step is that the data is copied from main memory to the local memory unit of the GPU. The data is then transmitted to GPU from memory of GPU. CPU sends the kernels to the GPU. Here, kernel is nothing but a function in terms of CUDA, and it instructs the GPU to process the data. GPU has multiple cores which execute the kernels sent to the CPU simultaneously. Next, once the parallelized process is completed, the result is then sent to the memory of GPU. The final result is eventually copied to the main memory. These are the CUDA programming steps. Some of the specifications are function qualifiers, CUDA built-in device variables, variable qualifiers, and in this we will also see the compilation, that is compilation phases and trajectory. Function type qualifiers in CUDA. The three main types of function qualifiers in CUDA are device, global, and host. First is device. The functions with device qualifier are executed on the device. These functions are callable from the device only. The second one is global. The functions with global qualifier are executed on the device, but they are callable from the host only. The next is host. The functions with host qualifier are executed on the host and are callable from the host only. When no qualifier is used, it means that the function will run on the host. It is equivalent to the function declared with the host qualifier. Variable type qualifiers. The three main types of variable qualifiers in CUDA are device, constant, and shared. First one is device. Stored in the global memory of the device, other type qualifiers are optionally used together with device. It is accessible from all the threads within the grid and host through the runtime library. It has the lifetime same as of the application. The second one is the constant. This qualifier is used to allocate constants on the device that are stored in the constant memory. It is optionally used together with device qualifier. This constant has the lifetime of an application. It is accessible from all the threads within the grid and host through the runtime library. The next one is the shared. This qualifier is used to allocate the shared variable. It is optionally used together with device qualifier, same like the constant qualifier. Shared variable resides in shared memory of a thread block and has the lifetime of a kernel execution. It is only accessible from all the threads within the block. CUDA built-in variables. These are the built-in variables that are readily accessible to all global and device functions. These are of five types. First one is grid dim. This has the dimensions of the grid in blocks and it has type of dim 3. And the next is block dim, dimensions of the blocks in threads and has type dim 3. And the next is block IDX, which has block index within the grid and has type uint3. Thread IDX, thread index within the block, and it has type uint3. And the last one is the warp size in threads, and it has a type of int. These are the CUDA compilation phases of 11.6.2, the latest version of CUDA, and there are four compilation phases for the latest version of this CUDA. First one is NVCC identification macro, which has different macros that are already predefined. The second is NVCC phases. This phase is required for the logical translation of the code. A single compilation phase can be further broken into smaller steps, which are just implementations of the phase, which depends on capabilities of internal tools that NVCC uses. But these may change for every new release of CUDA toolkit. Supported input file suffixes. The suffixes determine how NVCC interprets its input files. The next one is the supported phases. It's a list of phases where NVCC has the option to enable the execution of the phase. A default name for an output file is also generated when there is no explicit output file name specified. CUDA compilation trajectory. CUDA compilation works as follows. The input program is pre-processed for the device compilation and is compiled to CUDA binary, which are placed in a FAT binary. The input program is pre-processed once again for the host compilation and is synthesized to embed the FAT binary and transform CUDA-specific C++ extensions into standard C++ constructs. Then, the C++ host compiler compiles the synthesized host code with the embedded FAT binary into a host object. The embedded FAT binary is inspected by the CUDA runtime system whenever the device code is launched by the host program to obtain an appropriate FAT binary image for the current GPU. CUDA programs are compiled in the whole program compilation mode by default. This is a picture, high-level picture that shows how CPUs and GPUs can work together to advance the science and engineering fields. Let's say there is a developed code in Java or C or any other language. If the desire is to run the code faster, the GPU can analyze the code and let us know the hotspots where most of the CPU usage is occurring. Let's say the 80% of the code is being executed in 20 minutes and the rest of the 20% is being executed in 2 hours. You would want to optimize the 20% of the code, understand the convergence to CUDA, and now those switches that would improve the overall efficiency of the entire code. The green lines here shown are the hotspots and are being parallelized by the GPU. The other majority of the codes is non-intensive and is easy to execute. Here is the NVIDIA CUDA computing platform, parallel computing platform. It provides the programming approaches, development environment, open compiler toolchain, and hardware capabilities, which makes the job easier as everything is available through NVIDIA collectively. These are the tools that are available to accelerate applications. This is the 3 ways to accelerate applications. Those are libraries, OpenACC directives, and programming languages. Libraries, these are drop-in to accelerate the applications. OpenACC directives can be used to easily accelerate applications, and programming languages are used to achieve peak performance of the applications. Libraries are developed by NVIDIA engineers, best for the performance and are easier to use. Some of the NVIDIA engineers dedicate most of their careers to develop these GPU accelerated libraries that follow API standards and would need minimal changes to enable the acceleration of the applications. Libraries are blended with high-quality implementations of functions that are encountered in a broad range of applications. Ease of use. Using libraries enable GPU acceleration without in-depth knowledge of GPU programming. Drop-in. Many GPU accelerated libraries follow standard APIs, thus enabling acceleration with minimal code changes. Quality. Libraries offer high-quality implementations of functions encountered in a broad range of applications. Performance: NVIDIA libraries are tuned by experts. Here is an example of the libraries can be used. SAX plus Y is a simple function that is A times X plus Y. For CUDA, you just add coblas to SAX plus Y. Next step is to allocate memory using malloc and main copy as memcopy. This need to be compiled with cublas library in order to automatically copy the data from CPU to GPU, which parallelizes and helps you to do the calculations quickly. Here, CUDA is using cublas, which is an algebraic library that deals with matrices and vectors. NVIDIA libraries run everywhere from resource-constrained IoT devices to self-driving cars to the largest supercomputers on the planet. As a result, you get highly optimized implementations of an ever-expanding set of algorithms. Whether you are building a new application or accelerating an existing application, NVIDIA libraries provide the easiest way to get started with GPU acceleration. So we call it as an ecosystem of the libraries. OpenACC directives. These are similar to commands in your code. These are helpful in easily porting the numerical kernels to the GPU. The $sign here is for the acceleration symbol that tells the CUDA Fortran compiler to look at this code and the code inside it. That is called pragmas in order to optimize and accelerate the code on GPUs. And then the compiler code is then loaded to GPU. So this will be relied only on the compiler. OpenACC is more similar to OpenMP, but multi-threading is done on GPUs here. OpenACC, the standard for GPU directives. These are very easy to use and it is only commands in the code. Directives are open source commands that are helpful to deal with multi-core processors. These are very powerful as it can pull near complete parallel power of a GPU. OpenACC directives are easy to use and powerful as well. These are the examples of how much difference the ACC directives are making in these applications. 5 times the normal amount in 40 hours of real-time object detection, 2 times the normal amount in 4 hours for valuing the stock portfolios, 5 times the usual amount in 8 hours to understand the interaction of solvents and biomolecules. These are the GPU programming languages of CUDA. These have flexibility that libraries and OpenACCs cannot do. It helps to deal with inner loops of code, that is inside and outside loops, to figure out the best strategy to make full use of codes available to do computations. MATLAB has some library to port code to CUDA similarly to OpenC that can go deep into the code. For Fortran, you can use OpenACC. CUDA Fortran, these supports the latest compilers that support both. All these have own syntax and programs that you need to follow. In Python, there are many libraries to directly use CUDA Python libraries. There are many languages that helps either to generate encoders themselves or do something related to CUDA compilers. This is a snap from NVIDIA website showing the GPU computing applications. NVIDIA is not just a hardware firm but are working with various manufacturers, vendors, and developers to speed up the computing applications. They also develop graphic cards that improve gaming experience by creating high resolution and lifelike 3D experience. The graphic cards also help in visualization, rendering, and animations as well. These are some of the real-world applications of CUDA. Fast video transcoding. Transcoding generally is a complex procedure which involves trillions of parallel computations in which many are floating point operations. NVIDIA created Badaboom to harness the raw computing power of GPUs to transcode video much faster than ever. Medical imaging using CUDA, MRI machines can now compute images faster than ever possible before and for a lower price. Before CUDA, it is used to take an entire day to make a diagnosis of breast cancer. Now with the CUDA, this can take 30 minutes. In fact, patients no longer need to wait 24 hours for the result, which will benefit many people. The next is X-ray tomography. CUDA helps to reconstruct the X-ray CT data in order to extend its clinical applications. It involves parallelism in order to generate three-dimensional image volumes to reveal the internal attributes of the structure or specimen. Some more real-world applications of CUDA: oil and natural resource exploration. Using a variety of techniques, it is overwhelmingly difficult to construct a 3D view of what lies underground, especially when the ground is deeply submerged in a sea. Scientists used to work with very small sample sets and low resolutions in order to find possible sources of oil because the ground reconstruction algorithms are highly parallel. CUDA is perfectly suited to this type of challenge. Now CUDA is being used to find oil sources quicker. In the neural networks, CUDA platform helps to really speed up the computations by using GPU processor. It provides highly tuned implementations for standard routines such as pooling, normalization, and activation layers in neural network. In the raw field of computational sciences, CUDA is very advantageous. For example, it is now possible to use CUDA with MATLAB, which can increase computations by a great amount. Other common tasks such as computing eigenvalues or SVD decompositions or other matrix mathematics can use CUDA in order to speed up calculations. Advantages of CUDA: CUDA has several advantages over traditional general purpose computation on GPU using graphics APIs. Enormous increase in processing power over convention CPUs. Increase in power of GPU is harnessed by parallel processing. Cost, time, and logistical savings over the number of servers as researchers can use multiple GPUs at once. Wide variety of designs to serve creators' needs. Faster downloads and readbacks to and fro from the GPU. CUDA provides a memory region that is shared among the shared threads, which can be used as a caching mechanism. Complete support of bitwise and integer operations. Limitations of CUDA: CUDA has several limitations over traditional general-purpose computation on GPUs. CUDA-enabled GPUs supports only NVIDIA hardware. Possible bottleneck between the CPU and GPU due to latency in bus bandwidth. Single process runs across multiple memory spaces, which is different when compared to other language environments. These are the references of the sources that we use to put together this presentation. Thank you.